verify whether a function is a solution to a given differential equation. And now that we know how to look at what the solution to a differential equation might look like graphically with direction fields, and how to sketch direction fields, let's look at methods to start analytically solving differential equations. Now, what we're going to focus on first is how to solve the first order differential equation, which I'm going to write as first order DEs to save time. First order differential equations. Most generally, the first order differential equation can be written as some function of x, y, and dy dx equals 0. Now, this isn't how we're going to tend to be representing differential equations all the time. It might even look a bit foreign. You might not have seen it before. Let's just quickly break it down and see how it could make sense. So, let's think of some function of x, y, and dy dx. Maybe that function is that we have dy dx plus y minus x equals 0. In this case, we could also write our differential equation as dy dx equals x minus y, or y prime plus y equals x. These are all different ways of writing the differential equation that stems from dy dx plus y minus x equals 0. So I hope you can see this form. You can get any different ways of combining x, y, and dy dx, so you can reach all different first order differential equations. Now, what we're going to focus on for this video is a very special form of this first order differential equation. This is the form where we have that dy dx equals a function of x, f of x, times a function of y. F has to be a function of only x's. It could be x squared sine of e to the e to the e to the cosine of x to the 1/millionth power. This is fine. But it can have no y's anywhere. And similarly, g of y can be whatever crazy function you want of y, but it can have no x's in it. If we have a function of this form, then what we can do is we can solve it using the separation of variables. And for that reason, we call this differential equation a separable differential equation, separable first order differential equation. And this separable differential equation is going to be the topic of this video. How do you actually separate it? How do you actually solve it? So let me delete this and let's get to it. I'm going to show you two ways of thinking about how you could separate this equation and solve for y equals x implicitly. And then in the next video, I'm going to show you an example of a real separable differential equation and how we can actually solve it using the method that we'll come up with in this video. So method 1 is going to be a hand-wavy, just to say not so rigorous, way of manipulating symbols in this differential equation so that we get it into a nice form where we can integrate. So the idea of this method is, hey, this is pretty close to being able to be integrated, but we can only integrate, right? We can only integrate a function of some variable, maybe s, if we have a ds. And right now, if we were to just, we don't have that. So method 1 is a little bit less rigorous because it says treat this dy dx, this derivative, as a fraction with the component dx in the denominator and dy in the numerator. If we treat this as a fraction, we actually get something pretty nice. We can define a function h of y to equal 1 divided by g of y. And then we can say, okay, the reason I said 1 divided by g of y is because we're about to divide g of y on both sides. After we divide g of y on both sides, what we're left with is that dy times 1 over g of y, but I just named that h of y, h of y dy equals f of x times, and again, we're treating this as a fraction. I'm multiplying through by dx. Now, once we have it in this form, h of y dy equals f of x dx, we have it into an area now where we can apply this integral rule, where if we have a function, d, and then that variable that the function depends on, then we can just take an integral. So next, we say, all right, we can just integrate this. So if we take the integral of the left side, take the integral of the right side, we get that some big H, so I'll name this big H of y, which you can think of as being the antiderivative of h of y, plus some constant c1, equals big f of x plus some constant that we can call c2. Now that we have this, we have these two different arbitrary constants. Well, if they're really arbitrary, then we can just combine them into one constant, which leaves us with our conclusion that an implicit solution, remember what implicit means, is it's not explicitly solved for y. It's not y equals something. It is just a relation between x and y. But we get that relation, we get this implies the relation that big H of y equals big F of x plus some constant, where this constant is, you can think of being this arbitrary constant plus this arbitrary constant. Really, it's just a new arbitrary constant. So this is way number one to think about it. So we can call this method one the hand-wavy symbol manipulation method. So symbol manipulation, because that's really what we're doing. We're pretending that this dy dx is a fraction, and we're saying, all right, we can break it apart. And in general, in calculus, when you treat this dy dx as a fraction of differentials, sometimes it works, sometimes it doesn't. In this case, it happens to work, and now we're going to see why with a slightly more rigorous proof of why you can actually separate these two functions. So let's go on here to method 2. So method 2 is going to involve, again, defining, so let me just rewrite the differential equation that we have. We have that dy dx equals our function of x times a function of just y. Now, what we say is, again, we're going to define, so going to define function h of just y to equal 1 divided by g of y. And just as a quick side note, there is actually a way in math to write a definition like this. We could have also written, so this is an option that we had, we could have also written that h of y is colon equal, defined to equal 1 divided by g of y. These are both perfectly valid ways of writing it. So now that we have this definition, let's just quickly rewrite our differential equation as h of y times dy dx equals f of x. And now as the second step to our more formal method, let's just, instead of saying that we use symbol manipulation to get to some big H and big F, let's just think about those big H and big F and write them down. So we're going to write down the functions what we're almost writing but not quite is that big H of y equals the integral of h of y dy. This isn't quite what we're writing, because what we want to write is something more along the lines of using what we already know. So we're going to write that big H prime of y equals h of y. And this way we're sticking to the realm of what we know, because we're saying, all right, we're just assuming that there's some function whose derivative is h of y, and we're going to do the same thing for f. So we're going to say big F prime of x equals little f of x. And now, given these, we should be able to just substitute these into our equation. So we get that big H prime of y times dy dx, that this equals big F prime of x. And now let's think about what this y is, because whenever we have implicit equations, we often play hide and seek. We forget that there might be, or rather we hide that there might be, this y is actually a function. So we could rewrite this as h prime of y, but y actually is a function of x, right? And we know this because y is a function of x, because dy divided by dx is our derivative. X is the independent variable. Y is a function of x times dy dx. This equals f prime of x. So when we write it down this way, what this really starts to look like, this left-hand side, is just the chain rule. Because we have here h prime of a function, and then here we have the derivative of that function. So we might think about rewriting that left-hand side as the derivative with respect to x of h of y, which again is just going to be h prime of y times y prime. That's just the chain rule. And this is going to equal f prime of, not of y, of x. And again, I suppose we could be reminding ourselves here that this h of y is really, again, a function of x, which is why we're taking it with the derivative with respect to x. This is h of y of x equaling f prime of x. Now, if we have the derivative with respect to x of this function, h of y of x, is equal to the derivative with respect to x of this function, right? So we could, again, just rewrite this f prime of x as the derivative with respect to x of f of x. If we have this, we can say confidently then that the functions simply differ by a constant, because the only thing that could get deleted here is a constant, and this is just equivalent to what integration says. We could say these functions must differ by a constant, therefore h of y of x simply equals f of x plus some constant. And this is the same conclusion that we arrived at through our symbol manipulation method, but by assuming these functions in the derivative form, we're able to more rigorously prove, okay, we actually can get this h prime y of x using the chain rule into this form, and then prove that these two functions are related, which is the same as we got from the symbol manipulation again, but more rigorously. So with the concept of a separable differential equation in our minds, in the next video I'm going to talk about how we can actually solve one and then do an example.